we were discussing another way of demonstrating that there are limit cycle solutions to a given set of equations, and we introduced something called the Poincare-Bendixson theorem. In this theorem, you have to basically find two contours and define an annulus-like region and show that in the inner contour, all the flow is outwards, and in the outer contour, all the flow is inwards. You can show that, then the theorem will ensure that there is a limit cycle and that is confined to within this region, gray zone R, this annulus R. And there will also be some kind of unstable fixed points inside the inner contour. So we have taken this equation, which is a model of glycolytic oscillations, and we have done the analysis, and we found this outer contour, which is given by the dashed line, then the inner contour, which is basically a small epsilon size circle centered on the fixed point, right? And we also shown that if the fixed point is unstable, then the flow on the inner contour is outwards. So this way we were able to define this region, and we were able to show the oscillations. I mean, if you're interested, you can simulate these equations and verify for yourself that there are oscillations. So one more thing we'll look at today, one more way of showing limit cycles, which is limit cycles by bifurcation. There are several kinds of bifurcation which can show limit cycles or can show oscillations. We'll only look at two kinds of them. And so why is it relevant to neuron modeling? So if you remember, one of the basic things about a neuron is that, okay, so you know that neuron can be in two states. One is the resting state, where the voltage is a flat line, right? And even if you perturb it, it will vary a little and come back to the same baseline value. And then you have the excited state, where it shows the oscillations. Now, so in the resting state, the input current is small. Okay, so Ix is small or less than some threshold. In the excited state, Ix is greater than some threshold. Okay, so now we just think of them as two kind of discrete states, very distinct states. But if you imagine that as you vary Ix gradually, right, the resting state suddenly becomes an excited state. So which means it's a bifurcation. So imagine this. So let us say I have two graphs here. In the first graph, I show Ix as a slowly varying variable, which goes from some small value to a high value slowly, right? And let us say it hits the threshold here. Okay, so threshold is somewhere here. So then correspondingly, you can imagine how Vm would vary. So Vm could also be increasing very slowly, right, up to that point. And suddenly, until then, there's only slow variation. It's still a kind of stable point, right? But once input current hits that threshold, it will suddenly show oscillations. So that's a bifurcation. And at that point, you have hit a bifurcation. Now there's a classic. So we have seen bifurcations in one of the earlier examples where we took a two-dimensional system, a linear system, x dot is equal to x, where A is a 2x2 matrix. And we have seen how by varying the trace and the determinant, you were able to get various kinds of fixed points and various kinds of dynamics. And you can see sudden transitions, right, as you move over from one region to another region inside the bifurcation map. So similarly, we can define a bifurcation which will take you from a steady state to oscillations as you vary some parameter. Typically, the parameter is input current, right? So the kind of bifurcation that will produce this kind of a transition from a stable state to a fixed point to oscillation is what is called a Hopf bifurcation. Now, just to get an intuitive idea about how a Hopf bifurcation can be produced, let us take a small example. So let's start with again our simple harmonic oscillator, our favorite example for oscillations. Only thing is, let us add an extra term, this gamma, right? Now we will see how the solution changes as you vary gamma. So gamma is a parameter, x is a variable. So now you convert this to second degree equation, second order equation to two first order equations, x dot is equal to y and y dot is equal to minus gamma omega square x. Now you can see that the eigenvalues of this equation, this system, right, is given by plus or minus I omega root gamma. Okay, and this gamma, if it is a negative number, right, you have so you have a saddle node, and if it is in second, so yeah, whereas if it is positive, then you have two. So if it is a negative number, then you will have two real values. One is positive, one is negative. So you'll have a saddle node. So no oscillations. When gamma is positive, you will have two complex, two purely imaginary roots for eigenvalues, and therefore you will have center. So which means in this example, you can see that as a vary gamma from negative values to positive values, at the origin, you will see that suddenly the dynamics of the system, right, changes from having some kind of a fixed point to having oscillations. So that's a simple example. So basically, when the roots move from left side to right side and become complex conjugates, right, you can get oscillations. So this kind of a thing you might have also seen in control systems. I'm sure some of you are from engineering disciplines, and you might have studied something in control systems. So in a control system, when the poles of the system move from left side to right side, right, just when the point when the poles are crossing over the imaginary axis, you will find huge oscillations. And when they actually cross over to the right side, to the right half plane, you will find the oscillations blowing up, right, expanding exponentially. So similar to that, here when you move, when the eigenvalues move from left to right, and now you have complex eigenvalues, right, you will have at the point where you cross the imaginary axis, you can have oscillations. So there's a kind of bifurcation you see in this half bifurcation. It is also called Andronov half bifurcation in recognition of the people who have originally kind of observed this. And here again, there are two kinds of Andronov half bifurcation: the supercritical Andronov half and subcritical Andronov half. Right, let us see what they are. So, like I said, in case of in this bifurcation, the eigenvalues move from left to right at the point where they cross the imaginary axis, and right, you'll have oscillations, right, because of this bifurcation. So there are two kinds, supercritical and subcritical Andronov half bifurcation, and these two are representative equations. See, this kind of bifurcation can be observed in lots of systems, but at the point, so what is interesting is at the point of bifurcation, even a very complicated system can be reduced by some transformation to something very simple like this. If you look at the half oscillator equation that we discussed, very early on in the math classes in this course, it was originally given in the Cartesian form, but by transforming it to polar coordinates, we were able to get it into something like this. Not exactly this, but it looks something like this. So similarly, even very complicated high-dimensional systems, at the point of bifurcation, sometimes can be reduced to some standard, what are called canonical forms, like this. So this is a kind of canonical form for observing, for capturing or representing supercritical Andronov half bifurcation. So the R variation is like this: R dot is equal to mu R minus R cube. And you remember in the half oscillator also we had a very similar equation for the R dot equation. In the original half oscillator, the theta dot was constant. Theta dot is equal to omega is what we had, but here we are adding another term which is a function of R square. So you have omega plus BR square. Now how does this system behave? Let us look at that. So R dot is equal to mu R minus R cube. So I can write this as R dot is equal to R into mu minus R square. Right. So now if you can plot R dot as a function of R, right, as you vary mu, meaning I consider different mu values. If mu is negative, this graph, R dot versus R graph, will look something like this. You will have only one root at R is equal to 0, and other roots are imaginary. Okay, so because mu is negative. Now, so if you look at dynamics like this, r dot is equal to all this. If I start with a positive r, right, when r is positive, r dot is negative. That means it is r is decreasing, so you will move in this direction. Whereas if so you'll move in this direction. If r is negative, right, then r dot is positive, so r will increase. You will move in this direction. So basically, from the right side, when you are on the right side, when you're on the right side, you move to the left. The left side, you move to the right. So you'll always converge at the origin, which means origin is the only fixed point, and so r simply goes to 0. Right. So there is no oscillation, obviously. Whereas when mu is positive, something interesting happens. When mu is positive, the same curve now becomes like this. Because earlier when mu is negative, it had only one real root, other two roots are imaginary. Actually complex, purely imaginary. Purely imaginary. They're complex but purely imaginary. But when mu is positive, then you will have all three real roots. Okay, so you'll have one root at the origin like before, and one root at plus root mu, right, and another root at minus root mu. So then what happens? Let us look at this. If r is greater than root mu, right, so we are somewhere here. So then r dot is negative, so r has to decrease. So you go like this. If r is positive but less than root mu, then we are somewhere here. Then in that region r dot is positive, so that means r has to increase. So you go like this. So which means under these conditions, when mu is positive, if you start from anywhere, right, r value from anywhere, it will go towards plus root mu and stay there. Similar arguments can be made on the other side, but anyway, in this case, although the equation is given like this, in this equation r represents the radius, so it is positive, the polar coordinates, right? So only right side is relevant. So therefore, the system always tends towards an oscillation of radius root mu. So which means when you are transitioning from mu negative to mu positive, and when mu is negative, there is no oscillation. When you are just crossing over, mu is just cross over from a negative to positive. At that point, you will find a very small oscillation with an epsilon amplitude, right? And as mu keeps on increasing, the amplitude of the oscillation also keeps increasing as root mu. So which means the steady state value of r, right? Once our oscillation fully forms, steady state value is equal to root mu. For mu greater than 0 and for mu less than 0, it is 0. So this is a classic Hopf bifurcation or unknown Hopf bifurcation. Because for mu less than some threshold value, some critical value, there is no oscillation. The moment mu crosses that threshold value, there is oscillation. And we can also see this by doing more analysis. So suppose you take the polar coordinates and convert them into, so take this polar form, right, and convert that into Cartesian form, right? So x is equal to r cos theta, right? So therefore x dot is equal to r cos theta, r dot cos theta minus r theta sin theta. So if you do all this, right, you can you'll be able to write this in this form: ux minus omega y plus some bunch of cubic terms. Okay, similarly, if you take y equal to so it should be r theta, sorry. So theta dot here. So similarly, if you take y equal to r sin theta, you get expand this, and you will have mu y plus omega x plus a bunch of cubic terms. So if you linearize this system, that is, ignore the higher order terms, then you will have a is equal to mu minus omega mu, and again you will get this. You see this in this. These are the eigenvalues of the system. For mu negative, the real part is negative, so it will be a stable focus because it's a complex eigenvalues. The real part is negative, so it's a stable focus. And when mu is positive, it is unstable focus. Right. So just at that time of crossing, right, you will have oscillation. So in this case, we have seen that the radius of the oscillation increases with mu as root mu, right? And for mu less than that critical value, there is no oscillation. So this is how the amplitude grows. So under these conditions, if the bifurcation takes place, as you vary some input parameter, like for example the input current, right? As the current value crosses some threshold value, suddenly the oscillation starts. But the only thing is here the oscillation is interesting. It starts off as a very small oscillation, small amplitude oscillation, and gradually increases. So can somebody tell me, is this the kind of oscillation you will see in the neuron, or is the kind of oscillation you have observed in the Hodgson-Huxley model? Can somebody tell me? Anybody? Then Hodgson-Huxley, as you increase the input current, suddenly at some point you will see spikes. Sorry, something like that, right? So it seems to be like an Andronov Hopf bifurcation, but is it of this kind? Is it supercritical Andronov Hopf bifurcation? So what this graph is telling you is, in this kind of bifurcation, when the oscillations form, at the critical value, the amplitude is still very small. As you move away from the threshold value, the parameter moves away from threshold value. So here the mu is like the current, right? Just when oscillations form in the Hodgson-Huxley model, the action potentials are of a finite size. They're not epsilon size. They're not infinitesimally small. And as you increase the current, they don't change. The height doesn't change much. I mean, the frequency increases a little bit. Whereas in the supercritical Andronov Hopf bifurcation, when the oscillations form, they start off as so. For example, if I look at this point, it will be like small oscillation. We'll look at it here. It will be slightly larger oscillation. Look at here, even larger. That's not what you see in the Hodgson-Huxley model. The moment the oscillations form, they always form at a finite size, because the size of the oscillation there is the action potential amplitude. Okay, so it is a kind of Hopf bifurcation, but it's not supercritical Andronov Hopf bifurcation. There's a different kind of bifurcation which we need to see, right, to be able to understand what happens in the Hodgson-Huxley model. Okay, so that is how amplitude changes, like this root mu kind of a variation. So similarly, if you look at the time period, so the thing is, although in this kind of bifurcation, when the oscillations form, they form with a small amplitude, with epsilon amplitude, but the time period is not small, because until then time period is infinity, because there is no oscillation at all. That is, time period is infinite. But the moment oscillations form, the time period of that oscillation is not infinity, but that frequency is equal to, at the point of the birth of the oscillation, frequency is omega is given as the imaginary part, the lambda value, right? And that is imaginary part of the lambda value, that's omega, and that is a finite value, it's not close to zero. And as you move away from the critical value of the parameter, the time period also varies like this, increases like this, given by 2 pi by imaginary value of omega plus this mu minus mu c value. Time period also elongates. Okay, so that's the nature of this thing. So to understand this, I want to present a small analogy, just for like a fun analogy, to understand what is this kind of a Hopf, supercritical Hopf bifurcation. Imagine, you might have seen this Mexican hat, a kind of a hat just popular in Mexico. Hat looks like this. Suppose you're able to get a hat like this, and it'll have a hollow region here. So this is central part, which is like a hill, and around the hill there is a hollow. Okay, think of it like a moat, right? So now if you have a marble inside this hollow, and if you kind of shake the hat a little, this marble will roll around that whole hollow, right, around the hill. It will go round and round the hill. So kind of, if I look at a top view of this hat, it looks something like this, right? There's a circular path. A marble will be going around circular path. The central point of that picture is like the top of the hat. Okay, so that is unstable. It's unstable equilibrium, right? So if you are on a small perturbation, it will drop off to the sides, and that point is like this unstable fixed point. Whereas this circular path around which the marble will roll is like a stable limit site. This is a kind of right, map the dynamics you will see in case of the supercritical and no Hopf bifurcation. I am showing the same thing as a slice, as a cross section. Suppose you take this Mexican hat, you make a vertical slice and take the cross section of it, it looks something like this. This is the top of the hill, top of the hat, and my marble I'm putting here, this colorful, multicolored marble, is in this one of the in the side groove in the tunnel, right? And then it can go around this groove. But this is not the kind of fabrication we have seen in case of Hodgson-Huxley model. It is something even more subtle, and that is closer to what is called the subcritical and no Hopf fabrication. So to demonstrate this, we need slightly different kind of equations. In the supercritical, it is enough if you take up to the cubic nonlinearity in the R-dot equation. In the subcritical, you need slightly higher order nonlinearity in the R-dot equation. So here the R-dot equation is mu r plus r cube minus r power 5, and the theta equation is very similar. It's the same as the previous case. So here, let us see what happens when mu goes from negative value to positive value. If we take this equation, r dot is equal to mu r plus r cube minus r power 5. It looks a bit complicated because it's a fifth order polynomial. So if we make a plot of this, I've done this in MATLAB, the curve will look something like this. Okay, so there is a 1 0 crossing here, 1 0 here, another 0 here, another 0 here. This is when mu is negative. And you can imagine that I'm only showing the positive axis, positive x-axis, that is r is positive. Similarly, on the negative side, since it's an odd function, right, negative side also you will have one root at minus mirror image of this point, another root at the mirror image of this point. So finally, we'll have 5 roots, and which is natural because equation is a fifth order 5th degree polynomial, so it will have 5 roots. So what does this equation mean? This graph mean? So let me draw this in a slightly more dramatic fashion, right? Exaggerating the roots and the variation of the curve around the roots. So it has 3 roots, one at the origin, one at A, let us say one at B. So let us see what happens. So if I start from some value, let us say outside beyond B. Beyond B, the r dot, so the r dot is, this is r dot, y-axis is r dot. And I'm plotting the curve when mu is negative. So beyond B, r dot is negative. So if I start my initial value of r somewhere here, it will roll down to smaller values and settle at B. Because if I start from a value between A and B, right, then here in this stretch r dot is positive. So my r will increase and go to the same. So now you can see that r will tend towards B and stay there. So it means there's a limit cycle, a stable limit cycle at r is equal to B. Now what happens if I start from a value which is less than A but positive? Right? When it is less than A and positive, r dot is negative, so which means r will reduce, so it will go like this. Okay, and once you go to origin, it will stay there. And in fact, on the other side, since it's an odd function, it will look like this on the other side. Okay, so in this stretch, r dot is positive, so r will go down, go up. So origin is a stable point. So for this system, for mu is negative, origin is stable, right? So there is a stable fixed point at the origin, and r equal to B is also stable. It corresponds to stable limit cycle, but r is equal to A is the limit cycle, but it's unstable. So like this dashed circle. Whereas if you take mu positive, right, what happens is this curve changes a bit here, and this curve changes a bit here to something like this, right? And here you see that for mu positive, there's one root at the origin, another root at B, r equal to B. That's all. Okay, so there's the other root. What happens goes to imaginary value, so you don't see it in this plot. So r is equal to 0 now became an unstable focus. R equal to B corresponds to a stable limit cycle. Okay, so this is how it varies, right? For the supercritical and Hopf bifurcation, when mu varies from negative value to positive value, so negative value it is like this, right, and it is like this. Okay, so what happens in this case is if I start from close to less than a, r less than a, it simply go to the fixed point and stay there. There is one more limit cycle far from it, but you don't know it is there because if you start from anywhere here, you won't be able to go there. You will just come back to the origin and stay there. But when mu goes to positive, suddenly that intermediate fellow at r equal to a, that guy disappeared, right? Suddenly, so what happens is, if I'm, so in this case, what happens is if r is greater than b, I come down to b, r is less than b, I go up to b. So r is limit cycle. There's only one limit cycle that's stable. So no matter where I start from, I'll always go to that limit cycle, right? And what is interesting is that limit cycle has a fixed radius, right? Moment that forms, moment mu is just becomes positive. So what happens is when I go from negative mu to positive mu, this b value doesn't change much, but a will slowly move towards origin and merge with origin and disappear, right? So that this small stretch of the curve disappears. Because of that, this unstable limit cycle disappears, but a stable limit cycle which is always there at b, that remains like that only, it doesn't change. So therefore, when mu becomes positive, suddenly now I am able to go to b and oscillate at b. Okay, so this is the kind of things what you have seen in Hodgson-Huxley model, because as you vary the input current as a parameter, which is similar to mu here, for that current less than some threshold value, it doesn't have to be zero, some threshold value, there's no oscillation. But when it crosses a threshold, there is an oscillation of a fixed amplitude, right? And it doesn't start from zero amplitude. Not only that, as you increase the current, the amplitude also goes up. In fact, you have seen this. Actually, no, in the Hodgson-Huxley model, amplitude goes down a little, but just at that point, you have an oscillation which is of finite amplitude. To understand this, I have redrawn the Mexican hat picture slightly, just as an analogy. That if you want to play this game at your homes, you need to find a Mexican hat and a small marble, right? You can play some nice games. So in this case, I've taken the same Mexican hat, but I put a small dent on top, like a little dent. Right now, if I roll the marble, it will roll like before in the tunnel, in the groove here in the bottom. But if I put a small marble here, right, that's like a little valley, right, like a ditch. So here that's a stable fixed point now, because if I jiggle it a little from here, it will just go to a side and roll back to this bottom of this hole, right? So now if you look at the dynamics as shown in this top view here, in this case there is a stable limit cycle here shown with the thick white circle, an unstable limit cycle shown as the dashed in a circle, and then a stable fixed point. Okay, this is what happens when mu is negative. So therefore, if you start with a small amplitude, if it deviates a little bit from the origin, it will roll back to origin, which is like mu equal to negative. Okay, but if you, in this case also, there is a hidden limit cycle far from the origin. So if you can start with a slightly large amplitude of r initially, to give it a big kick, it will go to this big limit cycle. So this actually, it shows a property called bistability. It is bistable. It has two stable states simultaneously. It can either stay at the origin and on a small perturbation come back to the origin. That's a fixed point. But if you give it a sufficiently big kick that it will be able to jump beyond this dashed circle, then once it is here, it will go to this white circle. But if it is inside this, it will roll over into the, so very beautiful kind of behavior. Okay, so with that, let us stop the discussion of bifurcations. What I want to do is, with this, we have looked at two extra ways of dealing with limit cycles. One is the Poincare-Bendixson theorem. The other one is right? The other one is this Andrew-Hopf bifurcation. So with this, now we're in a position to look at a bunch of low-dimensional neuron models. The Hodgson-Huxley model is not only high-dimensional, it's also very complicated, very hard to analyze theoretically, right? Because it has 4 equations, and so therefore 4 variables, and they're all highly nonlinear. So that you cannot analyze theoretically. So what we'll do now is, because like I keep saying, if you want to simulate large networks, then your single neuron model must be sufficiently simple. So we have started with the Hodgson-Huxley model and then went to the biophysical modeling. Now we want to now step down to simplified neuron models. We'll start with something called Fujii-Nagumo model. So for that, let us see how we can start with the Hodgson-Huxley model and simplify it by making some assumptions. And then we'll be able to show limit cycles, etc. We can do phase plane analysis, use all the kind of arguments that we have shown in the last couple of classes, right? And then do some analysis and show limit cycles and things like that. So we have seen Hodgson-Huxley model. It has 4 equations. We will try to derive something called a Fujii-Nagumo model, which is named after the people who developed this, by reducing the 4-variable HH model into something smaller. So how do you reduce this? These are the equations of the Hodgson-Huxley model, and I'm not showing the explicit forms of the alpha beta functions. I mean, there's something there. Let's not worry about that. But they are static equations, so there are only 4 differential equations. So what we'll do now, we'll make some assumptions about the M, H, and N variables, and try to get rid of 2 of the variables. Right? How do we do that? So the basis of the assumptions is that the M, H, N variables apparently operate at different time scales. Right? So the standard trick in dynamical systems, by which people reduce multivariable dynamical systems into a small number of variables, is do what is called this variable separation. Right? So how do we do that? So apparently it turns out that M is a fast variable, because what is a fast variable? Let me, so if you remember your right, so we have seen the gating variables have this form. Right, so x infinity is a steady state value, and tau is the time scale at which x approaches steady state. So then what will be a fast variable? A variable which has small tau. Okay, so the taus are different for different gating variables. So that is the basis by which these people have succeeded in eliminating a couple of these equations. So since M is a fast variable, what that means, so thing is x tends to x infinity. If this tending takes a long time, then you have to simulate this differential equation and exactly find out how x tends to x infinity, because you know that it tends to x infinity like this. That is x infinity. This is x and this is tau. And the time constant here is tau. But suppose tau is small, then so if tau is, let's say, small, it will quickly tend to that steady state value. Okay, so this is x infinity. So if tau is small, then I can assume that x is approximately equal to x infinity, right? Because so x is a variable. I'll just assume that it is almost like a step function. It will quickly reach the value of x infinity. That's an assumption. So which means this equation on the left side is 0. So if I want to solve, so which means x equal to x infinity means minus x plus x infinity is 0, right? That means x dot is 0. In that sense, I'm saying this. So if I solve for this x equal to x infinity, the same thing here in case of M equation, M will be equal to alpha M by alpha M plus beta M, where they depend on the membrane voltage. So So by assuming that m is a fast variable, we'll replace the m dynamic equation, this dm by dt is equal to alpha v into 1 minus m, all that stuff. So this equation is replaced by this static equation. So the m dynamic equation is replaced by static equation. So what matters is only the dynamic equations. Static equations will not cause any problem. So similarly, the h variable in the Hodgson-Huxley model is a slow variable. So we'll just say h is, since it's very slowly, we'll say it's like a constant. So therefore h is approximately equal to some constant value h naught. These are assumptions that are reasonably valid, in the sense even with the assumptions you can show a lot of very interesting dynamical effects, right? So these two assumptions are the basis of the so-called Fujii-Nagumo model. And after making these assumptions and by plugging them into the original Hodgson-Huxley model, they did some more simplifications and they got rid of all those highly nonlinear transcendental functions like tan h's. We have a lot of the tan h functions among, which are used to describe the alpha beta functions. So they have cleaned up all that and approximated that, using Taylor series type approximations. They have reduced these very highly nonlinear transcendental functions, and they have taken only the smallest terms in that. And finally, they have come up with these two simple equations. So in case of Hodgson-Huxley, you have a voltage equation and three other equations describing the gating variables. Whereas in the Fujii-Nagumo model, there is a voltage equation, which is also very simple. V is the voltage, right? So dV by dt is equal to f of V minus W, which is a second variable, plus current. Okay, and this W is second variable, which kind of represents, so among m, h, and then we got rid of m, we got rid of h. There's only one variable left, n. So the so Vm in the original, sorry, let me erase this. So original Hodgson-Huxley versus Fujii-Nagumo, right? Vm here becomes this small v, and the n variable here becomes W in Fujii-Nagumo, and m and h is nothing, don't exist. Okay, sorry, m and h don't exist. Okay. So it's a two variable model consisting of this small v and W, and the V equation is dV by dt is equal to f of V minus W plus Im. Im is external current, and f of V is given by a cubic function, V into a minus V times V minus 1, and W is given by a linear equation. So very simple compared to all the transcendental functions which we have seen in the original Hodgson-Huxley. It is BV minus RW. So both B and R are positive. Okay, so V is analogous to the, remember what is W represents? Actually, the second variable. Other variables are implicit, they are hidden somewhere. Okay, so let us try to make a graph of this. The first equation f of actually, so if you look at the null lines, right, V dot is equal to, let me call this f of VW, and that is basically given by f of V minus W plus IA, and by setting this equal to 0, you get the f null line or V null line, right? So that looks like this, because it's basically a cubic function in V, and you see that the cubic function that we have seen also is like this. V into a minus V into V minus 1. You can see that this function has roots at 0 and A and V, and so if you look at the V cube term, right, most dominant term, V cube term, it has a negative sign. So for V large positive, right, it will be, this function will be negative. And since it has 3 zeros, so for large positive it should be negative. I should have 3 zeros. So sorry. So this is V equal to 0. This is V equal to A. And this is V equal to 1. Right? For a large positive, it is 1 to 0, 1 to negative. So since this is a 0, this is 0 crossing, after that it will go to positive. After that, V equal to 8 is again 0. So after that, it will be negative. Again, in the origin, it is 0. Okay, so this is how this function looks. It's a cubic equation. So after that, there's no more 0 crossing. It simply go to positive infinity here. So this is how this cubic equation, cubic polynomial looks. And if so the null line will be W is equal to the small f of V plus I external. I'll call this IA. So that is the plot we are seeing here. Okay. So if you increase this IA, basically that will shift this null line up. Decrease it, it will shift it down. So very simple. Similarly, if you look at the null line for the second equation, that is so this is, you can also call this the V null line. You can call this the W null line, right? So then what happens? It's simply a straight line. So very simple. And you see that so W null line is BV minus RW is equal to 0. You also write this as W is equal to V by R times V. So the slope of this straight line is V by R. Okay, so let us stop here, because so what we'll do is, we've covered a lot of math stuff. So next class, what we will do is we will so find out, we want to show basically the objective of Fujinoguma model is to capture the essential dynamics of Hodgson-Huxley model without using a much simpler set of equations, right? So by simply using phase plane techniques, can we show at least some of the basic properties of Hodgson-Huxley model? What are the basic properties? When current is less than some threshold, there should be no oscillations. As you gradually increase the current, when the current crosses a threshold, there should be oscillations, and so on. So at least this is a basic thing you need to be able to show. So we will see in the next class, using stability analysis and all that, how as you vary the input current and take it beyond a point, you will see oscillations. Another very beautiful result about Fujinoguma model is the generation of action potential. Even a simple set of equations like this, that will show how action potential can be generated, right? So this is the minimal nonlinearity that you need to produce action potential kind of a response, right? So we'll see all this on Monday, and so that's all I have for today. Any questions? So I'm aware I'm covering a lot of math, but if you ask questions, I can make it simple, because I think if you want to get into computational neuroscience in the future, for your higher studies or something, I think you need to have like a very broad understanding of different approaches, different methods used. You might be working only at high level, abstract level, network level, or doing very low level, single neuron kind of modeling, right? So that's why I'm trying to cover as much as possible. It's a very broad spectrum of ideas and concepts I'm presenting, right? So we'll cover these single neuron model, simplified neuron models for a couple of classes, and then we'll start the networks, discussion on networks. Any questions? Okay, no questions. Let's meet on Monday, and have a good weekend. Thank you.